Welcome back to Physics with Captain Rod. What I'm going to do here is just create a video here to kind of overview the concepts of this unit for you Physics 109 students. So this unit is really all about energy and work. All right, so let's kind of go over these quick. Energy is the ability to do work, and work is force times distance. So in essence, energy is the ability to apply a force to something and push on it and move it. Energy comes in two types, potential energy and kinetic energy. Right. Potential energy is energy due to position. Kinetic energy is energy due to motion. Now, as far as how these are calculated, your kinetic energy is always going to be 1/2 mv squared, and this is not going to change. Potential energies come in different types. The first type in physics that we usually talk about is gravitational potential energy. Right, this is equal to mgh as far as how it's calculated. But again, there are more coming. More coming soon. So, this is not the only equation, if you will, for potential energy. Now, a system has a certain total energy, which is the sum of these two things. So, if I write that out, right, my potential energy plus my kinetic energy is equal to the total energy of a system. This total can be changed via work. If I take this system, which has this energy, and then I do some work on it, I will now change it to a new energy. So I'm going to just put ones here and here to represent the total energy before work is done. PE2 plus KE2 represents the total energy after the work is done. Right? And the total that I start with plus any work done is equal to my new total. So this is what's known as the work energy theorem. It's probably the most important thing for this particular unit. And what we're going to do is we're going to use it to solve various problems in physics. Now, what was I going to say about this? Oh, this equation kind of looks long and complex, but I assure you it's not. Imagine maybe my classroom here. It's got a bunch of people in it. Now, how many? Don't worry. I know I've only got 3 in the picture, but let's say that it's got N1 people in it. Now, there's a door presumably somewhere. If I let some time go on, some people are going to go out the door, some people are going to come through the door. So what we're going to have here is that door is going to produce a change in N. So if I start with N1 and I add my change in N, I now have the new number of people in the room, which I might call N2, and this is just basic arithmetic. Now, I can take these n's here and get a little more detailed. I can break this N1 up into the number of females and the number of males, and I could write that N1F for the number of females at state 1 plus N2F, N1M representing the number of males, right, plus some sort of change, a delta N, number of people coming in or out the door. That's now going to equal my new number of females plus my new number of males. So you see that this equation basically looks just like this. The work energy theorem is just basic arithmetic applied to energy. Now, as far as how do we apply it, or even to back up further, when do we apply it? The work energy theorem, although it's always true, it's not always useful. In order for the work energy theorem to be useful, you need a problem where there are changes in potential or kinetic energy. So that's when we apply it, whenever we see kinetic or potential energy changing. I'll talk a little bit about how we apply it. You always identify what I call state 1 and draw it. And there's examples of what I mean by that. Go through, I probably got at least a half a dozen of them posted, or I will have at least half a dozen by the end of the day. You draw the system at state 1. You draw the system at state 2. You write out the work energy theorem, and then you just go through it term by term. When you're dealing with potential energies, you have to define what's called the datum. The datum is where you measure the potential energies from. Then the potential energy terms are going to be mgh terms. The kinetic energies are going to be 1/2 mv squareds. All right, this work term, these are going to be force times distance. And what you're looking for is some sort of external force doing work on the system. Now, In the overwhelming majority of the homework problems you have, I believe this work term will be 0. I'll go through and take a look at all of them. But for your homework for Unit 3, I don't believe there's any problems that have external forces. So this will probably be 0 for every problem that you work. And then your PE2 are going to be MGH terms, and these KE2s will be 1/2 MV squareds. So I think I'll save the examples for another video. I just wanted to kind of overview principles of work and energy here. And I've done that, so I'm going to end this now and make another one talking about your homework. Have a great day.